Hello, in this video we're going to take a look at a couple of examples of exponential functions. Our first one, we have the half-life of radium is 1,690 years. If 90 grams are present now, how much will be present after 410 years? So, the radioactive decay of chemical compounds is going to follow the formula A equal P e to the RT, where A is the amount left at the end, P is the amount at the beginning, R is the rate of decay, and in this case it's decay, so R is going to be a negative value, and then T is going to be our time. There's really two parts to this problem because we're not given the R. We know that the half-life is 1,690, and we want to know how much will be present after 410 years, but we don't know what that rate of decay is. So using this first sentence, the half-life of radium is 1,690 years. Half-life means that what we have left over is half of what we started with. So that is giving us the fact that A is equal to 1/2 of P. So 1/2 of P equals P times e to the R times our time value here is 1,690 years. We need to solve this for R. Our first step is we need to isolate that exponential, so let's divide both sides by P, and we get 1/2 equals e to, I'm going to go ahead and write this with the coefficient first as we normally see it. And then we need to get rid of that exponential. Since we have a base e, let's take the natural log of both sides, because the natural log of e to a power is going to simplify to just that power, giving us just that exponent, 1,690 times r on the left, or on the right, and on the left we get the natural log of 1/2. So our decay rate here is going to be the natural log of 1/2 divided by 1,690. And if you want to go ahead and plug that in the calculator, you can. We do not want to round this, however. We want to keep it as expanded as we can and as precise as we can. So we do not want to round that, but we can put it in our calculator and then just use our answer next time around. All right, so that's going to be our decay rate, and that is, as we saw here, a negative number, so it is decaying. If we start out with 90 grams, we want to know how much will be present at the end. So we're going to look for A when our P value is 90. Our rate that we just found was the natural log of 1/2 divided by 1,690 times 410 years, given in the question. And so now we can just plug in 90 times E raised to that answer. It's our R value, times 410 years gives us 76.07. And the units on that are going to be the same units that were given in the problem. So grams of radium. All right, our next example is dealing with Newton's law of cooling. Here we have a pizza pan is removed at 5 p.m. from an oven. The oven was at 425 degrees Fahrenheit, and it was put into a room that is a constant 73 degrees Fahrenheit. After 5 minutes, the pizza pan is at 300 degrees Fahrenheit. All right, so Newton's law of cooling says that our temperature at time t is going to be the temperature of our room minus, that should be plus the difference between the temperature of the original minus the temperature in the room times e to the negative kt. So here our U is going to be the temperature of the pizza pan. Our big T is the temperature of the room. U sub 0 is the original temperature, so when it came out of the oven, it was 425 degrees. K is going to be a constant that has to deal with the rate at which it is changing temperature. So that's going to be the insulation factor of what we're talking about. And then little t is going to be our time. And as long as we stay consistent, we can use any time units that we want. Our temperatures all need to be in the same units, but can be either Fahrenheit or Celsius. All of these are in Fahrenheit, so we'll stick with that. So this one we are going to have to do two pieces, very similar to what we did on the last one, because we've got to find that K value first. So it's removed at 5 p.m. That's not giving us a whole lot of time other than our original is 5 p.m. So if we want to find what time something's going to happen, it's going to be minutes after 5 p.m. Okay, the original temperature was 425. So this is giving us U naught. The room is 73 degrees, so that's giving us our big T. After 5 minutes, the pizza pan is 300. So that's telling us that U equals 300 when little t equals 5. All right, so let's first find that K value. So 300 equals 73 plus U naught was 425 minus 73 equals negative K times 5 minutes. All right, so let's go ahead and we can subtract 73. Let's see, 300 minus 73 is 227. 425 minus 73 is 352. We can divide both sides by 352. I'm going to go ahead and leave that. I don't know if that reduces or not, but I'll go ahead and leave it unreduced for just a minute because we're going to plug this in the calculator. And we need to get that exponential exponent down. So let's take the natural log of both sides. So we get the natural log of 227 over 352. The natural log of the exponential base e are going to cancel out. So we're left with just that exponent. So we get the natural log of 227 over 352. All of that is going to be over negative 5. So that is our K value. So that's a constant that is telling us how fast the pizza pan is changing in temperature. So if it's left in this room, at what time will the pizza pan be 130 degrees? Well, 130 degrees is going to be the temperature of the pan, so we're going to plug that in for U. Our temperature in our room is still 73. Our original temperature was still 425. T is still 73. Our K value is the K value that we just found here. I'm going to go ahead and leave that for K right now, but we do know what K is equal to, and then we're going to solve this for the time. All right, so 130 minus 73 gives us 57. We still have that 352 inside the parentheses. We can divide both sides by that 352. And then just like we saw on the previous part, we're going to take the natural log to get that exponent down. The only difference is now we know K and we're solving for T. So we get the natural log of 57 over 352 is equal to K times T. So our T is going to be the natural log of 57 over 352 divided by that K value, which is the natural log of 227 over 352 over negative 5. So let's go ahead and plug that in the calculator. I am going to do that in two pieces. And so I'm going to do that K value first. So the natural log of 227 divided by 352, close parentheses on the natural log, divided by negative 5. So our K value is 0.0877. And then we're going to do the natural log of 57 over 352, close parentheses on our log, and divide by that k value. Gives us a time of I made a little mistake here when we plugged this in. I've actually forgot that should be a negative k here, and a negative k, and a negative k, and a negative k, and it makes it negative k down here. So when we plug in, we're actually going to plug in by the negative version, so we are going to get 20.75 there. So this is approximately 20.75 minutes. So if it started at 5 p.m., that means that's going to be approximately, we'll go ahead and round that to the nearest minute, 5:21 p.m. All right, how long will it take for the pan to be 170 degrees? So we know our K value. Now we're going to plug in the exact same process that we just did for the 130, but now we're going to plug in 170. And we see that that 130 is going to affect this 57. So the only thing that's going to change in this problem is that 57, instead of being 130 minus, it's going to be 170 minus, so that'll be a 97. So we can go through that same process, or we can realize that this is going to happen almost the same thing over and over again. So we'll get the natural log of 97 over 352. And remember that 97 came from 170 minus the temperature inside the room of 73 over negative natural log of 227 over 352 over negative 5. So if we plug that in the calculator, we're going to get the natural log of 97 over 352 divided by a negative version of the answer that we had right here was our K value of 0.08. And we get 14.69 minutes. And this one wants to know how long, not what time. And so that right there would be our answer. And we do expect it to be something smaller than the answer that we got on the first part, because 170 is between the original 425 and the 130 that we did on that previous example. So what's happening to the temperature of the pan as time passes? And if you think about it, well, what would happen to a pizza if you left it on the counter at 73 degrees for as long as it could sit there? And you're going to see that it's going to start approaching the temperature of the room. And so as time goes on, it's going to get closer to 73 degrees, which is the temperature of the room. All right, I'll see you guys next time.